Hi, welcome to Unit 4, Day 1. This is Review Part 2, where we'll be reviewing periodic trends. So just to recap, periodic trends are patterns that are evident in the periodic table, and we looked at quite a few periodic trends before school closed. But before we get into those trends, I just want to remind you of the terms that we use when describing the periodic table. So remember, groups describe vertical columns. So for example, here, this is group 1 and shown in red, group 2 in orange, etc. And the periods describe the horizontal rows. So as you go across, this first row that we go across is period 1, second one would be period 2, and then period 3, etc. All right, let's dive right into the periodic trends. The first trend is the atomic number. So just to recap what the atomic number is, the atomic number is the number of protons in an atom, and it's the property of the atom that identifies the element. So what do I mean by that? That means that, for example, all hydrogen atoms and only hydrogen atoms have an atomic number of 1. So if an element has an atomic number of 1, you know it's hydrogen. If an element has an atomic number of 5, you know it's not hydrogen because only all hydrogens have an atomic number of 1. Okay, so let's take a look at what happens to the atomic number as we go across a period in the periodic table. And it's important to just focus on one period at a time. So here I'm focusing on period 4, and the atomic numbers are shown at the top. What do you notice is happening to the atomic numbers as you go across to the right? Do they increase or decrease? What about when we go down a group? What happens to the atomic number? So again, we're going to focus on one group at a time. And this time I'm focusing on group 1. What do you notice is happening to the atomic number as we go down? Great, so in both cases, going across to the right and going down, the atomic number increases. So that would be an example of a periodic trend. We notice that there is a trend in a property as we go across and as we go down. Let's look at our next periodic trend, valence electrons. So just to remind you what valence electrons are, they're the electrons in the outermost occupied shell of an atom. So let's take a look at an example with sodium. Sodium has an atomic number of 1. That means it has, 11. That means it has 11 protons. If sodium is neutral, it will have the same number of electrons, so it has 11 electrons. Okay, so here we have a Bohr model of sodium to show how those electrons are arranged. That first circle with no dots on it represents the nucleus. And then around that, we have these what are called the electron shells. And the electrons are shown as these black or red dots. So when we fill up the Bohr model, remember we start off with the first 2 electrons go in the first shell, because that shell can only fit 2 electrons. The next 8 can go in the second shell. That one can fit a maximum of 8. So far we used up 10. We have 1 more since sodium has 11 electrons, and that last electron will go in the third shell. So that third shell is our valence shell, and then that electron in that shell is called a valence electron. So in the diagrams you're going to see, the valence electrons are going to be shown in red. Okay, so what happens to the number of valence electrons, the electrons in the outermost shell, as we go across to the right in the periodic table? Once again, we're going to focus on one period at a time. So we focus on period 1. We start here with hydrogen. It has 1 valence electron. And then we go to the next one, helium. It has 1, 2. We can try the same thing in period 2, starting with lithium. It has 1 valence electron. Beryllium has 2. We skip the transition metals. Boron has 3, etc. So what's happening to the valence electrons as we go across? Now we're going to look at what happens to the valence electrons as we go down. So if we focus on one group, let's say group 1, if we will start with hydrogen, it has 1 valence electron. Lithium has 1, and sodium has 1. And remember, I know it has 1 because it only has 1 electron in the outermost shell. Those electrons are shown as the red dots. And you can try that for any other group as well. What do you notice? Great, so what you'll notice is going across to the right, the number of valence electrons increase, and they actually increase by 1. But as you go down a group, the valence electrons remain the same. So group 1, for example, all of these have 1 valence electron. Group 2 all have 2. One exception to that would be group 18, the noble gases. So helium has only 2 valence electrons, but the rest of them have 8. And the reason for that is helium's valence shell is the first shell, which can only fit 2 electrons. So the key thing is that you can determine how many valence electrons an element has just by which group it's in. So group 1 has 1 valence electron, group 2 has 2 valence electrons. We skip the transition metals, so group 13 to 12, we don't worry about their valence electrons. And then we hop on over to group 13, and group 13 doesn't have 13 but 3. Group 14 has 4 valence electrons. Group 15 has 5. So that's something important to know. Group 16 has 6. Group 17 has 7. And then group 18, remember, helium has 2 and the rest have 8. All right, let's try a quick CFU. So an element has 1 valence electron. Which group is it in? Pause the video now. When you press play again, the answer will be revealed. Great, it's in group 1. So anything in group 1 has 1 valence electron, or if something has 1 valence electron, you know it's in group 1. An element has 5 valence electrons. Which group is it in? Pause the video now. When you press play again, the answer will be revealed. Great, the answer here is group 15. So remember that we skip those transition metals. So if you said group 5, you were looking at transition metals. We skip all those. So group 15 is the one that has 5 valence electrons. Okay, our next trend was atomic radius. That describes the size of an atom. So the larger the atom, the larger the radius. So let's take a look at this diagram here. We have atoms. So you notice that they're different sizes. What happens to the atomic radius or size as we go across a period? And what happens as we go down a group? Great, you'll notice as you go across, the atomic radius is getting smaller, so it's decreasing, or the size of the atom gets smaller, so the atomic radius decreases. And as we go down, the atom size gets bigger, so it increases. So this is the atomic radius trend. The next one we're going to look at is electronegativity. And this one is actually super important for Unit 4. So what is electronegativity? It measures the ability of an atom to attract electrons in a covalent bond. And you can sort of think of that as the more electronegative the atom, the stronger it can pull. And a good way to visualize that, think about two dogs playing sort of tug of war with a toy. So these two dogs are about the same size, so they're going to be pulling on them equally. They have about the same electronegativity. Whereas on the other hand, in this example, the two dogs are not the same size, and one dog is going to be pulling on it more. So let's see if we can use our definition of electronegativity for this highlighted picture here. Which dog do you think would have a higher electronegativity, the white dog or the brown dog? And explain. Pause the video now, and when you press play again, the answer will be revealed. Okay, so the white dog, it's a larger dog, like it's stronger, so it's going to pull the toy, which represents the electrons, harder. So basically, the stronger the atom is in the tug of war, the more electronegative it is. So here we have electronegativity values. They're shown as the numbers below. The commas, by the way, represent decimal places. Oops, sorry. So this would be 2.20. So what I want you to do is I want you to take a look at the trends and see what you notice, what happens as we go across a period and down a group. Great, as you go across, you'll notice that the electronegativity increases, and as you go down, you will notice that the values decrease, electronegativity decreases. So a couple of key points. One thing you may notice is you're going across, the electronegativity stops at group 17, and the noble gases don't have electronegativity. And that's because noble gases don't form bonds, so you can't measure their electronegativity. So one thing to know is noble gases, we don't have values for them. On the other hand, the other thing to know is the three most electronegative elements are nitrogen, oxygen, and fluorine. So these are the three highest, with fluorine being the most electronegative. And the least electronegative would be these two metals here, cesium and francium. The next trend is the ionization energy, and that's the energy required to remove an electron from the outermost shell of an atom or ion. I like to think of this as like taking candy from a baby. So how much energy is it going to take you to remove a candy or electron from a baby? Not that much, because babies have a low ionization energy. They're not holding on to it very tightly. Whereas if you try to remove candy from an adult, try to take candy away from an adult, it would have a higher ionization energy because it's harder to take candy away from them. So ionization energy is the energy required to remove an electron. Now we can take a look at the trends that are shown here. The higher the column, the higher the ionization energy. So what do you notice as you go across a period, and what do you notice as you go down a group? So the ionization energy as you go across, it actually increases, and as you go down, it decreases. And it actually follows the same general trend as electronegativity. The only difference is electronegativity cannot be determined for the noble gases, but you can determine the ionization energy for the noble gases. So noble gases have the highest ionization energies. All right, last trend has to do with reactivity. So you may remember we talked about elements being reactive, and this is chemically reactive. In terms of metals, which are on the left side, the most reactive metals are the ones in the lower left corner, so where cesium and francium are. In fact, they're so reactive that if they were exposed to air, they would just explode. For the nonmetals, it's the one in the upper right corner, so fluorine would be the most reactive nonmetal. All right, so the most reactive metals and nonmetals are in their corners. The only exception, of course, are the noble gases. These are not, they are very unreactive. They're not reactive, they don't form bonds. All right, so here's a quick summary of the periodic trends. Notice that there are quite a few trends here: atomic radius, valence electron, etc., reactivity. So what are the ones that you absolutely need to know for Unit 4? The ones that are most important for Unit 4 are the valence electrons, electronegativity, and then the metallic and non-metallic character / reactivity. So these are the ones that you need to know for Unit 4. All right, that's it for this video.